Okay, so for this question, we're going to be naming the organic compound above over here. So we can see that in the centre here, we've got an ester functional group. And for naming esters, we have two parts to that name, and that's derived from the different sections either side of that ester group. So let's start over here on the right-hand side. So we've got 3 different carbons to this section. Therefore, we have a propyl group. And then on the left here, we've got 4 carbons, and that's including the carbon in that carbonyl bond there. So we need to make sure that we're including that bit in our name. So what we have here is the butanoate section of our ester. So overall, our answer is therefore going to be part B here, propyl butanoate for our answer. And that's how you answer this question. Okay, so for this question, we've got the setup to oxidise ethanol to ethanoic acid. And we've got our oxidising agent here, which is our acidified potassium dichromate solution. And we can see that we've got a reflux setup here in the diagram below. So what we want to investigate with this question is why are we actually heating this under reflux? So you can see we've got a few different options here. But let's actually think about what reflux setup is itself and why we actually need to use it. So for reflux, this involves heating the chemical reaction for a specific amount of time while continually cooling the vapours produced so they condense back down using this condenser here into liquid form at the bottom. So your vapours are continually being produced and rising and then getting condensed and falling back down to the bottom here. Now specifically for this reaction, we're going from a primary alcohol to a carboxylic acid. And as we know, with primary alcohols, we could also produce an aldehyde from our oxidation reaction. So if we don't get the condensation of these vapours, if they don't fall back down into this flask here, we won't get the continual reaction, which then goes from the aldehyde to our carboxylic acid here. Therefore, the reason that we need to heat under reflux is to prevent any substances escaping, to prevent any vapours leaving the mixture, and therefore allowing us to continue the reaction to completion. So the answer is option B, and that's how you answer this question. For this question, we need to work out how many stereoisomers we have for this compound here. So let's start by drawing this out. So we need to bear in mind for our stereoisomers that we've got 2 different types of stereoisomers to look out for. We have geometric stereoisomers, which occur across alkene carbon-carbon double bonds, and we also have optical isomers, which occur when there's a chiral carbon centre. And a chiral carbon centre is one where you've got 4 different groups attached to a carbon overall. So, looking at this compound here then, what we can see is that we've got 2 different double bonds here. So thinking about our stereoisomers, we're going to get stereoisomers for this double bond here, this region, but we're not going to get them for this end region. And the reason why is because this end one over here has got 2 of the same group attached to 1 carbon. Therefore, this will not have E or Z isomers overall. Now the second type of isomerism we need to look for is going to be our optical isomerism. So let's see if we have any carbon centres. So we're looking for a carbon with 4 different groups attached, and there's one here in the middle. So therefore in total we've got 2 stereoisomers from that double bond and 2 stereoisomers from that chiral carbon centre. Therefore our answer is going to be B, 4 stereoisomers in total, and that's how you answer this question. For this question, we need to identify what organic compound we have based off of 2 chemical tests. So from our list of options, we can see that W could either be an alcohol, as shown in A and C, a ketone, as shown in B, or an aldehyde, as option D here. So let's have a look at the 2 chemical tests we've got. So our first one is heating with our acidified sodium dichromate. So this is an oxidising agent, which can be used to oxidise primary and secondary alcohols or aldehydes. And our second test is the addition of 2,4-dinitrophenylhydrazine, also known as 2,4-DNP. And this is the test for a carbonyl bond, which is found in either an aldehyde or a ketone there. So therefore, we've had a positive result for the first test and a positive result for the second test. So our answer will have to be option D, because that is an aldehyde. So therefore, we'll get oxidized with this oxidizing agent, and we'll also have a positive result for that carbonyl bond there. And that's how you answer this question.
This question follows the complete combustion of a gaseous hydrocarbon and uses gas volumes to identify the formula of hydrocarbon X. So we've been told that we've got 40 centimetres cubed of our hydrocarbon and that this requires 240 centimetres cubed of oxygen and produces 160 centimetres cubed of carbon dioxide. We've also been told that all of these gas volumes are at room temperature and pressure, and what we know is that when we've got our gas volumes at room temperature and pressure, the volume ratio is going to be equal to the mole ratio in the equation. So let's write out a general combustion equation so that we can identify our mole ratios and hence work out the formula of X. We've got our hydrocarbon X reacting with oxygen to produce carbon dioxide and water. Yeah. So now let's start to look at some of these mole ratios to identify the ratios within the equation. We've been told that we've got 40 centimetres cubed of hydrocarbon X, and therefore the ratio of X to our carbon dioxide, we've got 40 to 160, and this goes down to a 1:4 ratio. Therefore we've got 4 moles of carbon dioxide, and this means that as we've got 4 carbons from that carbon dioxide, our hydrocarbon X will also have to have 4 carbons. Therefore, we can eliminate options C and D, and our answer will have to be either A or B. So let's have a look at some more ratios to figure out the rest of the formula. So now, let's have a look at the ratio of the hydrocarbon to oxygen. So again, we've got 40 centimetres cubed of our hydrocarbon, and this requires 240 centimetres cubed of our oxygen. And this ratio goes down to a 1:6 ratio. So now we can put a big 6 in front of our oxygen, and this must mean, so overall we'll have 12 oxygen atoms on the left-hand side. We've then got 8 oxygen atoms from that carbon dioxide on the right-hand side. Therefore, 12 minus 8 must mean that we have 4 oxygen atoms from that water due to the conservation of mass. Therefore, we can put a big 4 in front of our water, meaning that we have 8 hydrogen atoms from that water. Therefore, because the only source of hydrogen on the left-hand side is our hydrocarbon, that must mean that our hydrocarbon has to contain 8 hydrogens. Hence our answer is option A, C4H8.
For this question, we've been given the boiling point of butan-1-ol as 118 degrees and the boiling point of 2-methyl propan-2-ol as 82 degrees. And we need to find out why butan-1-ol has got a higher boiling point than 2-methyl propan-2-ol. So let's start by drawing out the structures of these. So butan-1-ol, we've got a 4-carbon chain with the alcohol group on carbon number 1. And for 2-methyl propan-2-ol, we've got a 3-carbon chain with our methyl group on carbon number 2 and our alcohol group on carbon number 2 as well. So what we can see here is that we've got a pair of structural isomers. Therefore, they're going to have the same molecular formula, hence they will also have the same number of electrons. See, they're both alcohols, so they're both going to have hydrogen bonding. And we've got a primary alcohol for our butan-1-ol, and our 2-methyl propan-2-ol is a tertiary alcohol. And we know from our reactions of alcohols, for example, the oxidation, that tertiary alcohols are much more stable than primary alcohols, and that tertiary alcohols will be oxidized. Therefore, the reason that butan-1-ol has got a high boiling point is because it's a straight chain structure. Therefore, it's got stronger induced dipole-dipole interactions because those chains can pack together closer. So your different chains can fit together closer, hence their induced dipole-dipole interactions are stronger. Therefore, our answer is going to be B. For the reaction of hydrogen bromide with 3-methyl-butyl-1-ene, we want to determine what the structure of the major intermediate formed in this mechanism is. So for this reaction, we've got an electrophilic addition mechanism. So we're adding on the hydrogen bromide across the alkene double bond. So let's start by drawing out the 3-methyl-butyl-1-ene so that we can then determine what our intermediate structures will be. So our 3-methyl-butyl-1-ene, we've got a 4-carbon chain, our double bond is across carbon 1 and 2, and we've got a methyl group on carbon number 3. So when we add our hydrogen bromide, we have the hydrogen orientated towards that double bond because of the dipoles, and we get our electron flow from the double bond to that slightly positive hydrogen. And we can form two different intermediates because the hydrogen atom can either add on to carbon number 1 or carbon number 2 because we've got an unsymmetrical alkene and we've got an unsymmetrical reagent. Therefore, we can get two different intermediates and therefore two different products. So our two different intermediates are going to look like this. So we've got two different carbocations, and using Markovnikov's rule, we can find out which one is the most stable carbocation. So Markovnikov's rule states that the most stable carbocation is going to be the secondary carbocation overall. So this one here on the right is going to be our secondary carbocation because that positive carbon ion is bonded to two different carbons, whereas this one on the left is a primary carbocation, therefore it's not as stable. So our answer will be B.
In this question, two chemical tests are carried out on an aqueous solution of an aromatic organic compound Y. We want to use the results of these tests to identify the minimum number of carbon atoms on the aromatic compound Y. So for it to be an aromatic compound, it's got to contain a benzene ring. So let's start by drawing this out for our first part of the structure overall. Now our benzene ring contains 6 carbon atoms to start us off. So now let's have a look at the results of the tests in order to identify how many other carbon atoms we might need to add on. So first off, our first test is that bromine water has been decolorized. Now we know that benzene alone does not decolorize bromine water because it's not electron dense enough to induce a dipole in the bromine, so it can't react with bromine unless there is a halogen carrier. But what we do know is that phenol, which has added electron density, can decolorize bromine because it can induce a dipole and doesn't need a halogen carrier. So let's add on our OH to make this a phenol here, and this hasn't added on any other carbon atoms yet. So then for our second test, we've got some sodium carbonate aqueous, and we've been told that we've got effervescence. So for this sodium carbonate, this is a base, and for there to be effervescence, this means it's reacted with an acid of sorts. We've had an acid plus our sodium carbonate, and this will have produced a salt, water, and carbon dioxide gas, which is causing this effervescence mentioned. Now the phenol here is only weakly acidic, so whilst it can react with sodium hydroxide, it can't react with sodium carbonate because it's not acidic enough. Therefore, in order to react with that sodium carbonate, there must be some sort of organic acid on this benzene ring. So we can add in a carboxylic acid functional group, and this adds in an additional carbon here. So we're now up to 7 carbons. Therefore, our answer must be B, 7 carbons, because we're looking for that minimum number overall. In this question, bromine is reacted separately with both nitrobenzene and phenylamine. Now these are both examples of our electrophilic substitution of that benzene ring overall. So we need to predict whereabouts this substitution will occur and therefore which organic products are going to be likely to form overall. So let's start by drawing out both the nitrobenzene and phenylamine so that we can predict which groups they will direct to. Our nitrobenzene, we've got a benzene ring with a nitro group on, like so. And our phenylamine, we've got a benzene ring, but this time with an amine group, an NH2 overall. So for our nitrobenzene, the nitro group is going to be a 3-directing group. And this is because it withdraws electrons from the ring, therefore deactivating it. So we're going to get substitution occurring at position number 3, which is going to be here, or could also be on this side as well. Whereas with our phenylamine, we can get substitution at positions 2 or 4. So again, could be over here. And this is because our NH2 group donates electrons into the ring. Therefore, it activates the ring, hence it's a 2,4 directing group overall. So we're going to be looking for the line in the table which shows the correct substitution. So for our nitrobenzene, we need to have 3-bromonitrobenzene. And with our phenylamine, we're looking for that 2-bromophenylamine. So overall, our answer is going to be C. Which alcohol could be used to prepare this organic compound here? We can see from the structural formula that we have an ester functional group in the centre, and esters are made up from carboxylic acids or their derivatives and an alcohol. So let's draw out the structure of this ester so that we can identify which alcohol could be used to prepare it. So we have our ester bond here, and a carbon, a hydrogen, and 2 methyl groups either side. We can see that we've got a 3-carbon chain in this section, and splitting that bond in the middle, we can see that the part containing the oxygen single bonded is going to be our alcohol derived section. So with our 3 different carbons, we would have to have some form of propanol as our answer. So it can't be D. Our answer can't be C, because this will be a propanol but also with a methyl group. And whilst we have got the 3-carbon chain, we don't have an extra methyl group there. We eliminate option C, so it could either be propan-1-ol or propan-2-ol. Now we can see in our structure that this O is bonded to carbon number 2 in the chain. Therefore, originally, this alcohol would have been propan-2-ol. It would have looked a bit like this here, with our OH on carbon number 2, like so. So our answer is B, propan-2-ol. We are told that cyanide ions react with haloalkanes and with carbonyl compounds. And we need to identify which row in the table is going to give us the correct mechanisms for the reactions. So first, we need to identify whether our cyanide ion is acting as an electrophile or as a nucleophile. So to recap, an electrophile is going to be an electron pair acceptor, and it's normally positively charged. And a nucleophile is going to be an electron pair donor, and it's normally negatively charged or has a lone pair of electrons overall. So looking at our cyanide ion, we can see we've got this negative charge, therefore we have a nucleophile overall. So our answer in the table is going to have to be one where the cyanide ion is acting as a nucleophile in both of the reactions. Therefore, just from this information alone, we can see that our answer is option D, but we can confirm this by double checking that our cyanide ion acts as a substitution for the haloalkanes and as an addition reaction with the carbonyl compounds. So let's have a look at a couple of examples just to confirm this. So with our haloalkanes overall, we have a delta negative, for example with this chloroethane, and this gives us a delta positive carbon due to the differences in electronegativity. So if our cyanide ion comes in, we can draw a curly arrow here, and then we lose that chlorine overall. So your cyanide ion substitutes out the halogen. Therefore, we've got a substitution reaction. So let's now have a look at our carbonyl compound reaction. So I'm just drawing propanone here as an example, and we've got differences in electronegativity again because the oxygen's more electronegative than the carbon, so we can draw in a dipole. So now our cyanide ion is again going to be attracted to that positive carbon centre. We then get a movement in a pair of electrons, and that opens up that double bond. So we're adding on to the double bond overall, and we end up generating a tetrahedral intermediate, like so. And here we can see we've gone from our trigonal planar to our tetrahedral, and we've added across the double bond. Therefore, we've got an addition reaction. So we've confirmed that our answer must be option D.
The structure of a molecule that is used as a pain reliever is shown below here. And we need to deduce which statement about this molecule is not true overall. So let's run through each of these answers and see what we've got. So for the first answer A, it has a molecular formula C8H9NO2. So let's count up the atoms in our molecule to see if this is correct. So our number of carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8. That's correct. Our number of hydrogens, we've got 3 here, we've got 1 here, and then we've got 1 on each of these and 1 over here. So in total we've got 3, 4, 5, 6, 7, 8, 9. So that's matching up. We've got 1 nitrogen here, and then we've got 2 oxygens overall. So this statement is correct, therefore it can't be our answer. So statement B, it reacts with bases to form salts. So looking at our functional groups on the molecule, over here we've got a phenol, and that's where you've got an alcohol group directly bonded to that benzene ring. And phenol groups are weakly acidic because the lone pairs on the oxygen are partially delocalized into this benzene ring. Therefore, this is a donatable proton. So it's weakly acidic, therefore it will react with bases to form salts. So this statement is correct, therefore it can't be our answer. Statement C, it has a ketone functional group. So looking at our molecule, we've identified that we've got a phenol here. And on a first glance, this might look like a ketone, but actually this carbon, rather than being bonded to an alkyl group, is bonded to a nitrogen. Therefore, this functional group, instead, is going to be an amide. So this statement is not correct, therefore that is going to be our answer C, but let's just check the last statement just in case. D states that it can be hydrolyzed with aqueous acid. So as previously mentioned, we've got an amide functional group here, and we know that amides can be hydrolyzed down the middle to produce a carboxylic acid and an ammonium-based compound with its aqueous acid. Therefore, statement D is correct, so our answer is definitely C. Carbonyl compounds have distinctive smells, and this compound below, menthone, smells of peppermint. We are told that menthone is reacted in a two-step synthesis. Step 1 is where our sample of menthone is added to hot acidified aqueous dichromate ions. And step 2 is where this resulting mixture from step 1 is then added to sodium tetrahydridoborate in water. And we want to know what happens to the smell of the reaction mixture during this process. So let's take a look at our compound of menthone. So we can see that we've got a carbonyl bond here, and in particular, this is going to be a ketone functional group because we've got a carbonyl bond surrounded by R groups in total. So this carbon is directly bonded to alkyl groups either side. And what we want to figure out is when this ketone will react, because when it reacts, it will no longer be a carbonyl compound and it will lose its distinctive smell of peppermint. So in step 1, we're told that we're adding it to hot acidified aqueous dichromate ions, and we know that this is an oxidizing agent. However, our ketone can't be oxidized under these conditions, Therefore, our smell of peppermint will remain after step 1. Hence our answer is going to have to be either A or C. So we can eliminate B and D. Now step 2 is where this resulting mixture is added to the sodium tetrahydroborate. So we know that our resulting mixture will be the same as before because our ketone has not reacted with the oxidizing agent. And then in this situation we have hydride ions from this compound which can come and react via a nucleophilic addition reaction, like so. And we end up forming an alcohol overall. The rest of the molecule either side, like so. We've reacted out the carbonyl bond, therefore we're going to lose that distinctive smell of peppermint. Hence our answer is going to have to be option A overall. And that's how you answer this question. Which of the following statements supports the delocalized model for benzene rather than the Kekulé model for benzene? So let's draw out the delocalized model and the Kekulé model, and then we can see which of these statements is correct overall. So our delocalized model of benzene is where we have our 6-carbon ring and the electrons are in a pi delocalized system which we represent as a circle inside the ring, whereas the Kekulé model is where we have 3 pi double bonds, and we sometimes show this as being alternating as well, like so. So let's have a look at these statements and see which of these are correct. So the first statement is that benzene is less reactive than cyclohexene overall. So we know that with our reactions of benzene compared to cyclohexene, benzene reacts via electrophilic substitution and requires a halogen carrier. For example, the reaction of benzene with bromine requires a halogen carrier, such as aluminium tribromide. And that's because the benzene is not electron dense enough to induce a dipole into the bromine. Whereas with cyclohexene, which has this structure here, this is an alkene, and this will decolorize bromine water because it reacts with the bromine directly via an electrophilic addition mechanism and does not require any catalyst or halogen carrier. Therefore, yes, benzene is less reactive than cyclohexene. So let's look at statement number 2. A benzene molecule has a planar hexagonal structure. Now, whilst this statement is correct, this doesn't support the delocalized model for benzene rather than the Kekulé model, because both of these have got planar hexagonal structures overall. So therefore, whilst this statement is true, it doesn't support the delocalized model for benzene rather than the Kekulé model. So let's have a look at the last statement. The enthalpy change of hydrogenation of benzene is more exothermic than predicted from the Kekulé structure. So this statement is actually incorrect. The enthalpy change of hydrogenation of benzene is less exothermic than predicted from the Kekulé structure. So the Kekulé structure, we would expect our enthalpy change of hydrogenation to be roughly 3 times that of the cyclohexene due to those 3 different pi bonds. However, it is much less exothermic than that overall. So this statement is incorrect and does not support our answer. So the only statement which is correct is number 1. Benzene is less reactive than cyclohexene, and this supports our delocalized model as opposed to our Kekulé model, where we would expect the reaction to be similar to that cyclohexene. Therefore, our answer is going to be D, only 1. The structure of molecule Z is shown below here, and we need to determine which of the following statements are true. So let's go through each of these statements, and then we can work out which ones are true. So the carbon-13 NMR spectrum of Z shows 4 peaks. The proton NMR spectrum of Z shows 5 peaks. And the third statement is that the proton NMR spectrum of Z run in D2O shows 3 peaks overall. So let's go through each of these one by one. So statement number 1, the carbon-13 NMR spectrum of Z shows 4 peaks. Carbon-13 NMR, the number of peaks is equal to the number of different carbon environments within the molecule. So in our molecule, we've got 1, 2, 3, 4 different carbon environments. Therefore, we're going to have 4 peaks overall. So this statement is correct. So statement number 2, the proton NMR spectrum of Z shows 5 peaks. So similar to carbon NMR, except this time we're looking at the number of proton or hydrogen environments. And here we've got 1, 2, 3, 4, 5 different proton environments. Therefore, we're going to have 5 peaks as well. So statement number 2 is also correct. So the last statement is that, same again, so proton NMR spectrum, but this time run in deuterated water. So this is D2O, an isotope of hydrogen here is known as deuterium, and it's heavier. And when we run our spectrum in D2O, any hydrogens which are bonded to either an oxygen or a nitrogen, so these different environments here, will be replaced by a deuterium atom. And deuterium does not show up in NMR spectra for proton NMR, therefore the peaks for these environments will disappear. So we started with 5 peaks originally, but 2 of our environments were protons bonded to an oxygen or a nitrogen. Therefore, 5 minus 2 means we will have 3 peaks left overall. So statement number 3 is also correct. Therefore, our answer is A, 1, 2 and 3, correct. Methyl allyl chloride, MAC, is a chemical used in the production of insecticides. We can see the structure of MAC here below. And we need to give the molecular formula of this compound here. So our molecular formula is our actual whole number ratio of the atoms within the compound. And we can see that we've got carbons, hydrogen and chlorine within our compound. So let's count up the numbers of the different atoms. So our carbons, we've got 1, 2, 3, 4. That's C4. For our hydrogens, we've got 1, 2, 3, 4, and then that makes 7 there overall. So that's C4H7 so far. And then we've got 1 chlorine. So our overall molecular formula is C4H7Cl, like so. The next part, we need to draw the skeletal formula of MAC. So for the skeletal formula, we show the carbon-hydrogen backbone as zigzag lines overall, so something a bit like this overall. So we don't show any hydrogen atoms at all. We only draw an atom if it's not a carbon or a hydrogen, so a different functional group overall. So let's draw this out here. So we can see we've got 1, 2, 3 carbons as our main carbon backbone. So let's draw that in like that. We've then got another methyl group up here, so we can add this on here. We've then got the double bond to add on between carbons 1 and 2, and then we need to add in our chlorine atom because that's not a hydrogen, so therefore we can draw that in as a bond. For the last part, we need to state what's meant by the term structural isomers. So our structural isomers are compounds which have got the same molecular formula but a different structural formula overall. And the key thing here is to include both of these parts for the mark. So you have to say both parts or you won't get the mark overall. And that's your 1 mark question for this part here. MAC is highly flammable, and when it burns, one of the products formed is a toxic gas. And we've been given some information and we need to identify what the gas is. So we've been told that 1.321 grams of this gas occupies 1.053 decimeters cubed at pressure of 100 kilopascals and a temperature of 350 Kelvin. So with this information here, we can use the ideal gas equation, which is PV equals nRT, and we can use this equation to identify the moles, because once we've got the moles, we can then use our mass in order to identify the molecular mass, which will be equal to the mass divided by the moles. So let's start by rearranging our equation for the ideal gas equation to work out the moles. So our moles is going to be equal to the pressure and the volume divided by
the gas constant R, which is in the data book, times by the temperature overall. Now the key thing with our ideal gas equation is to make sure that we're using our standard index units. So this is going to be pressure in pascals, temperature in Kelvin overall, and volume in meters cubed. So we need to make sure that we convert some of our data here above to the correct units. So 1.053 decimeters cubed. To convert that to meters cubed, we just have to divide it by 1,000 overall. So we will have 1.053 times 10 to the minus 3 meters cubed. And then next we need to convert our pressure into pascals. And to go from kilopascals to pascals, we just multiply by 1,000. So therefore we have 100,000 pascals as our pressure. And our temperature is already in Kelvin, so we don't need to worry about converting that. And the gas constant you can find in your data book, and that is going to be 8.314 joules per Kelvin per mole overall. So now we can plug in our numbers. So our moles is going to be equal to 100,000 pascals times by 1.053 times 10 to the minus 3 meters cubed, all divided by 8.314 for our gas constant, times by 350 Kelvin. And if you pop this into your calculator, this will give you a value of 0.0362 for our moles overall. There. So now our next step is to use our moles and our mass, which was given to us at the beginning, to work out the molecular mass of this toxic gas. So the molecular mass is going to be equal to 1.321 grams divided by 0.0362 moles overall. And this comes to a value of 36.5. Now to try and identify this gas here, we know that when we burn hydrocarbons, we normally produce carbon dioxide and water, and if it's incomplete combustion, we also could produce some carbon monoxide and some carbon particulates. But our compound MAC has got this chlorine atom in it. And chlorine has got an atomic mass of 35.5. And a toxic gas which we've come across before could be HCl. And this has a mass of 36.5 because it's 1 from the hydrogen plus our 35.5 from the chlorine, which gives us 36.5. And that would make sense because we've got a source of chlorine in our compound MAC. Therefore, our gas is going to be hydrogen chloride, HCl. And for this question, there was a mark for the working out with the ideal gas equation, a mark for identifying the moles of the gas, 1 mark for the working out of the molecular mass of your gas, and then the final mark was for identifying that the gas was HCl overall. The flowchart below shows some of the reactions of MAC, which is this compound here. And we need to complete this flowchart by drawing the structure of the product of reaction 1 and the structure of the minor organic product of reaction 2, which is compound B overall. So let's start with the product from reaction 1. We've got our compound MAC here, and our reagents is hydrogen and nickel. And this reaction is going to be a hydrogenation reaction where we open up this double bond and instead we saturate the compound with hydrogen. So our compound will look like this. So we've got our 2 carbons in the middle, we've still got our CH2Cl, our methyl group up here, the 2 hydrogens from the original compound, and then we're adding on 2 additional hydrogens. So we've ensured that each carbon has still got 4 bonds, and we've now saturated this compound. So it's got the maximum number of bonds that it can get around each atom. We've saturated it with hydrogen. So now the structure of the minor organic product of reaction 2. So these reactions are electrophilic addition reactions, and we've got the reaction with HCl over here overall. And this is going to, again, add on across this double bond. So we can see that with the major product, we've added on our chlorine to this carbon here and our hydrogen to this carbon here. And the reason why this is the major product is because it would have gone via the most stable intermediate. So the intermediate would have been via the most stable carbocation, which would have looked like this overall. So a carbocation is where you've got positive charge on a carbon. And the reason why this is the most stable carbocation is because it's a tertiary carbocation overall. So we've got 3 different carbons bonded to the specific carbocation, therefore it's tertiary. So this is the most stable intermediate. So therefore, the minor product will be where instead we've got the charge on this carbon here, so the other atom from that double bond. So that will look something like this overall. So this time we've added our hydrogen on to the second carbon, therefore leaving us with the positive charge on this carbon here, and this carbon has only got one other carbon attached. Therefore this one is going to be a primary carbocation, which is less stable, hence why it's the minor product overall. So the product will look like this. So it's where we've got the Cl bonded where that charge was, like so. And there is 1 mark for each of the compounds overall, giving us 2 marks for this part of the question. Now, as we've identified, our reaction 2 gives us a mixture of the compounds. And we've identified that compound A is the major product. And now we need to draw a mechanism for the formation of compound A overall. And we need to ensure that we're using our curly arrows and that we're showing any relevant dipoles here for this question. So let's start out by drawing our MEC compound, and then we can start to add in some curly arrows and some dipoles to follow this reaction. So this is going to be reacting with HCl, and this is an electrophilic addition reaction where our HCl is acting as an electrophile, and the reason why is because the chlorine is more electronegative than the hydrogen, therefore generating a permanent dipole where we've got our partial charges on these atoms. Therefore, the slightly positive hydrogen is going to be attracted to this electron-dense double bond region over here. And it's an addition reaction because we're adding onto that double bond. We're opening up the double bond and adding new bonds in overall. So let's start to look at some curly arrows now. So for our curly arrows, we need to identify the source of our electrons and then where those electrons can flow onto. And each curly arrow with a double arrowhead represents the flow of 2 electrons overall. So our source of electrons is going to be this electron-dense double bond region here. And they are going to flow onto that slightly positive hydrogen. Now this is going to form a bond, and hydrogen can only form 1 bond overall. Therefore, the bond between the H and the Cl is going to break. So that electron pair is flowing onto this chlorine. The electron pair is already slightly closer to the chlorine anyway because the chlorine is electronegative. And it's important in our diagrams that our curly arrows are going from the direct source to where we want them to go. So we have to be really clear with each end of the arrows and where those are flowing to. This is then going to generate our intermediate, which we drew above, but we're going to draw it again here so that we can then add in the rest of our arrows. So we've added on our hydrogen to this carbon here. So we've got a carbon with 3 different hydrogens. And then let's draw in the rest of our compound. And then now we've got an electron deficient carbon. We've produced a carbocation here because this carbon has now lost its bond here. It's lost these electrons. Therefore, it's positively charged.
Now, what we also produced in this section was a chloride ion when we flowed these electrons onto this chlorine. So we've now got a carbocation, we've got a negatively charged chloride, and this is going to therefore attack that carbocation there. So those electrons are going to be flowed onto that carbon, forming a new bond. And therefore, we're going to produce this compound here. And this is going to be our major product because it's gone via the most stable intermediate, the most stable carbocation, which is the tertiary carbocation, because the carbon has got 3 other carbons bonded to it, making it the most stable. And for this question, there was a mark for drawing the first arrow here from the double bond to the hydrogen. The second mark was for drawing the dipole on the HCl and for drawing this second bond here, which was breaking the bond between the hydrogen and the chlorine. And then the third mark was for drawing your curly arrow in this intermediate here, showing that chlorine going to that carbocation overall. Explain why compound B is the minor product of reaction 2. So reaction 2 was the electrophilic addition of HCl to our compound MAC, and our minor product was the one where the chlorine was bonded to carbon number 1. And the reason why this was the minor product was because it went via the least stable intermediate. So it's because it had the least stable carbocation intermediate overall. And you need to say all of those points in order to get this mark for this question. Now we are told that MAC reacts with water in the presence of aqueous silver nitrate and ethanol. And for this question, we need to draw the structure of the organic product, state what we would observe in this reaction, and identify the compound responsible for the observation overall. So with our compound MAC, this has got a chlorine atom overall. And when we react it with water in the presence of aqueous silver nitrate and ethanol, we're going to get a hydrolysis of this bond here, and therefore we're going to get a substitution where the chlorine is replaced by a hydroxide ion, therefore giving us this compound here as our product overall. So we've just substituted out the chlorine with a hydroxide overall. And what we would observe would be a white precipitate overall. And that is because when we get our hydrolysis of this bond, we're going to produce some chloride ions. And the test with our silver nitrate is the test for chloride ions. And that's because we get a reaction between these, a precipitation reaction, where we produce silver chloride, which will be that white solid, that white precipitate. And for this question, there was 1 mark for the structure of the organic product and 1 mark for identifying that we've got a white precipitate as our observation and that the compound responsible for this was silver chloride. So you need both of those last points in order to get that second mark overall. Compound A reacts slowly in humid conditions to form compound C. We are told that compound C contains the following percentage composition by mass. So we've got 46.1% of carbon, 7.7% of hydrogen, and 46.2% of oxygen. We are also given an infrared spectrum of our compound C, which is shown here. And for this question, we need to use all of this information to deduce what the structure of compound C is overall. So the first thing to note is that we've got humid conditions. So this tells us that we've got some source of water, which is going to be
a source of oxygen and hydrogen. So that's something to bear in mind here when we're thinking about our compound C, which only contains carbon, hydrogen, and oxygen. We can now look at our percentage compositions by mass because we can use this data to work out the empirical formula of compound C overall. So let's start by setting us up a table. So we'll need our percentages, our moles, and our ratios. And because we've got the percentage composition by mass overall, we can use the formula of moles equals mass divided by atomic mass. So where we're using our percentages as the masses here, each of these parts overall. So let's start by filling in our percentages. So we've got 46.1% of carbon, 7.7% of hydrogen, and 46.2% of oxygen. So now let's work out the moles of each of these parts. So for carbon, we need to divide this by 12, which will give us a moles of 3.84. For hydrogen, we need to divide this by 1, which gives us a moles of 7.7. And for oxygen, we need to divide this by 16, which gives us a moles of 2.89. And all of these atomic masses can be found in your periodic table in your data booklet overall. So now we need to work out the ratio of each of these atoms to each other. And we can do this by dividing each of the moles by the smallest mole value. So we need to divide each of these by 2.89 in order to work out that ratio. So when you divide each of these values by 2.89, you get a ratio of 1.33 for carbon to 2.66 for hydrogen to 1 for oxygen overall. Now, for our empirical formula, we need to have the simplest whole number ratio. And we haven't got whole numbers here, but they're also a little bit too big for us to just round up and down. But what we can see here is that we've got some form of a third here. So if we times these all by 3, we could potentially get to some whole number values. So if we now times each of these by 3, we come to values of about 4 to 8 to 3 overall. So therefore, our empirical formula is going to be C4H8O3 for our empirical formula. So now, let's take a look at our infrared spectrum of compound C. And there are a few key peaks in the spectrum which we can point out. There are 3 peaks here which are standing out. And we can remember that everything between around about 500 until 1500 is going to be our fingerprint region. So we can't actually identify any clear peaks from this region because it's quite noisy, it's quite messy, but each individual compound has its own unique fingerprint region, like a fingerprint itself. So now, if you use your data booklet to look at the transmittance and the wave numbers, so the different wave numbers for these peaks, we can identify this peak here. So that's the peak at around about 3,450. This is going to belong to the OH from an alcohol overall. We've also got this broad absorption between about 2,500 and 3,300. So this is a broad absorption, which is key. And this is going to be the absorption which belongs to the OH from a carboxylic acid functional group overall, so from this OH here instead. And finally, the other peak which stands out is this sharp absorption here. So this is between around about 1,640 and 1,750, and this is going to belong to the carbonyl bond from our carboxylic acid overall as well. So it's time to put all of this information together now. So looking back at our empirical formula, when we compare this to our compound A, they've got the same number of carbons. So therefore, a good deduction to make would be that this also would have the same number of carbons, hence this is also going to be our molecular formula. So if we draw in our carbon framework then to start us off, we're sticking with the same number of carbons, it's humid air, so a good deduction to make would be that our carbon framework won't be affected too much. And now we identified from our infrared spectra that we've got a carboxylic acid functional group and an alcohol functional group. And that totals up to 3 oxygens in total. So we've got 2 from the carboxylic acid, 1 from the separate alcohol, and that matches up with our empirical formula over here. So now it's just time to tie all of that together for an overall structure. So it would be a sensible deduction, because our original compound contained 2 chlorines, but compound C does not contain any chlorines. So these are probably going to be the areas which have changed in terms of where we're replacing the chlorines with our new oxygen-based functional groups. So we could put our alcohol group up here. So we're just substituting that chlorine out for the alcohols. That'd be a substitution reaction. And for this section here, to turn into our carboxylic acid overall. So this would give us a final structure that looks like this overall. So just adding in our atoms and then the rest of the hydrogen atoms, and let's just count up and check that we've got the right number of hydrogens. So we've got 4 carbons, we've got 3 oxygens, and for our hydrogens we've got 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 hydrogens in total. And for this question, there was a mark available for the ratio, a mark available for the empirical formula. There was 1 mark available for identifying the alcohol absorption in the infrared spectrum. And then for the 4th mark, we had to identify the absorption from the OH that belonged to a carboxylic acid and the absorption belonging to the carbonyl bond for the carboxylic acid. So we had to have both of those mentioned for the 4th mark. And then the 5th and final mark was for the structure overall. Molecules with more than one functional group are useful chemical building blocks. Compound D, the structure shown here, is an intermediate in the synthesis of a variety of drugs. We are told that compound D can be synthesized from ethanol, which is an aldehyde, and we need to devise a 2-step synthesis of compound D from ethanol, ensuring that we give details of any reagents and conditions required, as well as giving an equation for each step showing clearly all of our organic compounds overall. So compound D, we can see that it contains an alcohol functional group and an amine functional group here. And we need to start from ethanol, which is an aldehyde overall, and it contains a carbonyl bond at the end of the molecule. So what we know about the reactions of our carbonyls are that they can undergo nucleophilic addition reactions. And we can see that the main difference between our structure of ethanol and our structure of compound D is we've added on this nitrogen group towards the end, this amine group. We've got a source of nitrogen and we've now got an alcohol instead of a carbonyl bond. So in order to have gone from the ethanol to compound D, we will have need to have undergone a nucleophilic addition with either some hydrogen cyanide or some sulfuric acid overall in potassium cyanide. And generally, this second option is preferred because hydrogen cyanide is quite a nasty reagent overall. And with this second option here, by using that sulfuric acid and potassium cyanide, we make the HCN in situ overall. So that means that it's made in the reaction mixture, so we're not actually having to handle it itself. So by adding these reagents to our ethanol, what we're doing is we're undergoing that nucleophilic addition reaction with the cyanide ion acting as our nucleophile overall. So let's write out an equation for this, and remembering that our key reagent is the hydrogen cyanide, but that's made in situ. So our key equation is going to be our ethanal. So the structure of the ethanal, we're using structural formulae here to make sure that we're clearly showing all of our organic compounds. Reacting this with our HCN, remembering that our cyanide ion is acting as a nucleophile, and this is added on to our ethanal, and we end up reducing that carbonyl bond to an alcohol and adding on that cyanide overall. And the way that this works is something a little bit like this here. So I'll just draw out the structures to make it clear of the reaction, and we get an attack in here, attack up there, and then the negative oxygen ion there reacts with the H plus from that HCN overall. And that's how we form this compound. So this is going to be our intermediate reaction. So now looking at the difference between this intermediate compound and our compound D, the only difference is between these nitrogen-based groups at the end. So we've currently got a nitrile on the end of our intermediate, and we need to go from a nitrile to a fully saturated amine and carbon-based group here. So to do this, we're going to need to add some hydrogen, and we're going to need a nickel catalyst for this reduction reaction overall. So the equation will be our intermediate of the same structure we drew out above, like so, adding in our hydrogen, our nickel catalyst over the top there, and then we produce our compound D overall for this one, like so. And for this question, we have a mark for our first set of reagents, a mark for our first equation, another mark for our second set of reagents, and a mark for that second equation there. Explain why compound D is very soluble in water, and we need to use a diagram in our answer. So let's start by drawing out the structure of compound D in a more detailed displayed formula overall. So what we can see from our structure is that compound D contains an amine group and an alcohol group overall. And what we know about both of these groups is that they contain lone pairs on the oxygen and on the nitrogen overall. And therefore, because these electronegative atoms are also bonded to hydrogens, these will be able to form hydrogen bonds with water. And because we've got two groups which can form those hydrogen bonds, that means that it's going to be a very soluble compound in that water. So let's draw out some of these hydrogen bonds overall. So we've already added in our lone pairs, and now we're going to start by drawing on the bonds like so. So the lone pairs, you then have your hydrogen bond, and then that's going to a delta positive hydrogen, which is delta positive due to the more electronegative oxygen on there, like so overall. This one. So we've drawn some hydrogen bonding here, and the key thing in our answer is to say that we have two groups which can form hydrogen bonds on our molecule. And the key thing is that it can form hydrogen bonds with the water overall. And for this question, we have a mark for saying hydrogen bonds somewhere in our answer with that water. That's a key thing. It has to be hydrogen bonding with the water as opposed to just within the molecules itself. And then a mark for drawing on each hydrogen bond. We are told that compound D reacts with propane dioic acid, with the structure here, to form a condensation polymer. And we need to draw out a possible repeat unit of this condensation polymer, showing clearly any functional group that's present in the repeat unit. So when it states that we need to show clearly any functional group, this means that we need to draw out our compounds. We can't just write it down in our molecular formula. We need to be really clear with the structures of these compounds. So with our propane dioic acid, this is where we've got a carboxylic acid group at either end of the molecule. And this can react in two places on our molecule of compound D. It can react with the alcohol group here to form an ester, or with the amine group here to form an amide. So we're going to have an ester group and we're going to have an amide group in our compound. So this is from our OH and our carboxylic acid, and this one's from our amine and the carboxylic acid as well. So there are actually two possible repeat units for this condensation polymer. So we can either center it around an ester bond, or we could center it around the amide bond. So we'll draw out both options so that we can see each of those. So let's start by centering it around our ester bond. So what I'm just going to do to start off is I'm just going to draw out compound D in a more clear displayed formula to the side so that we can see exactly where we're going to be forming our ester bond overall. So when we're forming this ester bond, that's going to be bonding from here. So this hydrogen is going to be replaced and we're going to form an ester bond there. So the structure will look something a bit like this overall. So we need to show the whole repeat unit as well. So this is the unit that will get repeated along the polymer chain. And here is our ester group. And then what we've got as well is an open amide group. So this shows that our unit will repeat, so we can put an N there as well if you like to show that it's repeating. And here's our ester functional group in the middle. So this part here was from the alcohol with the amine, so this part here was from compound D, and this part here was from our propane dioic acid, like so. Now alternatively, we could also center it around an amide bond. So instead of showing a split amide bond, we could have the amide bond in the center, so just slightly drawing this in a different configuration. So this is where we're going to lose a hydrogen from this amine group, and then this will bond with the propane dioic acid there. So it's bonding in the same way, we're just drawing it out in a slightly different way. So we could look like this, or we could have our ester bond split outside of brackets, and then we could center our molecule around our amide bond in the middle, like so. And here we've got, this time, an open ester link, and this is the other option you could have for your repeat unit. And for this question, there is 1 mark available for drawing both the ester and the amide bond. So you need to have both of those in there in order to get that first mark. And then the second mark is for drawing the rest of the structure correctly. Serine, with the structure shown below here, is an amino acid. So that means we've got an amine group and we've got an acid group here and a variable R group at this end here. And for this question, we need to use the electron pair repulsion theory in order to predict the shapes of the bonds around atoms A and atoms B, which are shown in the diagram. We also need to give our bond angles around atoms A and B, and we need to give reasons for all of our answers. So we need to use this electron pair repulsion theory in order to explain our predictions overall. So atom A is going to be this nitrogen atom here, and atom B is this carbon atom I've just circled. So let's start with atom A. So looking at this nitrogen atom, we can see that we've got 3 bonds overall. So we've got a bond to that carbon and a bond to each of these hydrogens here. So that means that that nitrogen has got 3 bonding pairs of electrons. But we know
that nitrogen is in group 5 overall from our periodic table. So that means it's got 5 electrons in its outer shell. Therefore, if 3 of those have been used for bonds, that means we've also got a lone pair of electrons on that nitrogen there. So in total, we've got 3 bonding pairs of electrons and 1 lone pair of electrons overall. And therefore, from our electron pair repulsion theory, we know that we've got 4 pairs of electrons in total, so this shape is going to be based off of a tetrahedral, but because we've got a lone pair, we know that lone pairs repel more than bonding pairs. Therefore, our shape is slightly different, and it's going to be a pyramidal shape overall, with a bond angle of 107 degrees, which is slightly less than that of the tetrahedral bonding angle, which is about 109.5 overall. So let's have a look at atom B now, which is this carbon. So whilst we've got 4 bonding pairs overall around this carbon, we've got 3 bonding regions only. And that's because 2 of those bonds are going to the same atom. So we've got that carbonyl bond there, we've got this double bond. So whilst we've got 4 bonding pairs, we've only got 3 bonding regions. And carbon is in group 4, so it's got 4 electrons in its outer shell, which are all used up in these bonds. Hence we've got no lone pairs of electrons. And from our electron pair repulsion theory, we know that if we've got 3 bonding regions and 0 lone pairs, that means we've got a trigonal planar shape overall around that atom, with bond angles of 120 degrees there. And for this question, there is a mark available for the shapes. So in order to get the marks for these shape and angles, it's 1 mark for giving the shape and the angle of atom A. So you need to have both the shape and the angle for this mark. There's also a mark for, again, the shape and the angle of atom B. So you need to have both of these bits in order to get each mark. And then there's a mark there for the explanation of the shape around atom A, and the final mark is the mark for the explanation of the shape around atom B overall. A student adds an excess of aqueous sodium hydroxide to a sample of solid serine, the structure shown here below. The student then purifies this resulting reaction mixture to obtain a pure sample of an ionic organic product. So for this question, we need to draw the structure of our ionic organic compound, which we've obtained, and we need to outline the steps that our student could carry out in order to obtain this pure sample of our organic product from the reaction mixture overall. So our solid serine here, this is our amino acid. And what we know about our amino acids is they've got this carboxylic acid group over here on the end. And because this is an acid, we're going to get an acid-base reaction with our sodium hydroxide, and we're going to form our salt and our water. And this ionic salt is the compound which we need to purify at the end. So this is our donatable proton here from the acid group. And this is going to get pinched by the hydroxide ions from that sodium hydroxide. And what we're going to form is going to be our negative ion. So we've got a negative organic ion here where we've lost our acidic proton from that acid group. We've got a negative charge now on that oxygen. And therefore this forms an ionic compound, so an ionic salt with the sodium ions left behind in solution overall. And we also form water, which I'll just pop in brackets there. So we've formed an ionic solid salt overall. So we're going to be making a salt solution because we've got this salt dissolved in this water. So what we can do in order to obtain a pure sample
is we can filter the solution as our first step. And then once we've obtained our solid, we're going to want to recrystallize that. And that's so that we purify our sample overall. And for this question, we've got 1 mark allocated to the structure of our ionic organic compound, 1 mark for saying to filter the solution, and the last mark is for stating that we need to recrystallize our compound in order to purify that so that we get that pure sample which the question was looking for. Tab toxin, the structure shown here below, is a poisonous substance which is produced by bacteria found in lilac trees. And for this question, we need to identify the chiral centres which are present in a molecule of this tab toxin overall. So first off, let's think about what a chiral centre is. So a chiral centre is going to be a carbon with 4 different groups attached overall. So we need 4 different groups bonded, and we can't be having double bonds, so it's not just 4 bonds, it's got to be 4 different groups overall. So let's have a look at our molecule and see how many we can identify here. So working our way from left to right, the thing we need to bear in mind is that this compound is drawn out in skeletal formula, and this is commonly done just so that the molecule looks a bit clearer, especially when we've got larger organic compounds to deal with. But what this means is that we're not going to see any of the hydrogens from our carbon backbone framework. So we can draw these in when we're working our way down if we think we've got a chiral centre to double check. So working from left to right, we've got a chiral centre here because we've got an additional hydrogen. So this is going to be a chiral centre because we've got those 4 different groups attached overall. We've got another chiral centre here. Again, we've got a hydrogen, we just can't see it, but that's also going to be a chiral centre with 4 different groups attached. Now, this group and this group will not be chiral centres because we've got 2 of these bonds going to an oxygen in here. So we've not got 4 different groups overall. So these will not be chiral centres. And this one here was not a chiral centre because there are 3 bonds to hydrogens at the end. So that's a CH3 at the end there, so that can't be a chiral centre. Our next chiral centre is going to be this one here. Let's draw in that hydrogen. We've got 4 different groups, so that will be a chiral centre. We'll mark that with an asterisk. Working our way along, these 2 can't be chiral centres because they're both CH2s here. So they've got 2 bonds to hydrogens, therefore they've not got 4 different groups attached. But this carbon here will be a chiral centre, even though it's in a ring, because it's got different groups attached either side. Therefore that will be a chiral centre. Now the only other carbons we've got will not be chiral. This one, as mentioned, can't be chiral because it's got 2 bonds to an oxygen, and this one here is another CH2, so that won't be a chiral centre. So overall, we've got 4 different chiral centres, and you need to have all 4 marked on with an asterisk in order to get that mark there. We are told that tab toxin can be broken down by alkaline hydrolysis, and we need to draw the structures of all of the organic products of the alkaline hydrolysis of tab toxin. So let's think about where this can be hydrolyzed. So parts of this molecule that can be hydrolyzed will be the amide groups. So alkaline hydrolysis, this breaks down ester and amide bonds. In our compound, we've got 2 amide bonds that can be broken down. So we can split up our molecule here, and we can split up our molecule here overall. Now this will only give us 2 different products, even though we've got 2 splittings, and that's because one of these splits is opening up a ring. So that won't actually form 2 different structures, it just opens up that ring to form 2 chains overall. So let's start now to draw out the structures of our products. So I'm just going to draw them out in skeletal form as we were
shown in this question already to make it a bit easier. So we've got a group here, and what we've formed is going to be a negative ion up here. And the reason why is because we've got our acid group, and this proton is donatable. And because we've got the alkaline hydrolysis, the alkali, so a hydroxide ion, is going to pinch this hydrogen here. Therefore, we're going to form a negative ion, which will be some sort of salt overall. We've not been given the specific alkali, therefore it's okay to leave it as a negative ion. So that's going to be our first product. And our second product, we're just drawing from here onwards. So this is where we're going to get originally it would be an acid group like this. But as I mentioned, because we've got an alkali, we're instead going to have this shown as a negative ion overall because that donatable proton will react with the alkali. So let's draw in the rest of our molecule now overall. And then for this last bit, we're opening up that ring structure. So we've got an NH2 here where we opened it up from the left-hand side of that bit. And then we've got our carbonyl and another negative oxide ion there overall. And for this question, there was 1 mark for drawing the structure, which was from the left-hand side here, so from splitting up that amide bond for this left-hand fragment. And then there are 2 marks available from the slightly larger structure from this right-hand fragment here. And the 4th and final mark is for having these oxide ions here, so for showing them as negative ions rather than acid groups overall. The student investigates reactions of aromatic compounds. The student first carries out the reactions shown below. So this is the reaction of quinol, which is an aromatic compound, with 2-methyl 2-chloropropane, a halogen carrier of iron trichloride, and we're producing this substituted compound E. So we've substituted one of the hydrogens on quinol with our compound here, and we're also producing some HCl overall. And this reaction, where we're adding on a carbon-based compound to our aromatic compound, is one of our Friedel-Crafts reactions, just for reference. And we are told that the student contains a very low yield of this compound E here. And we are told that the student obtains a much higher yield of a different organic product with a molecular formula of C14H22O2. And we need to suggest an identity for this organic product, and we need to draw its structure below. So first, let's work out the molecular formula of our compound E, so then we can see how this new organic product is different to compound E. So compound E contains carbon, hydrogen, and oxygen only. So let's go through and work out the molecular formula for that. So for carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 carbons there. For hydrogens, we've got 1, 2, 3, 4, 5, and then we can add on 9 overall from this group over here. So overall we've got 14 hydrogens and we've got 2 oxygens there overall. So we can see that the main difference between the molecular formula of compound E and our organic product here is going to be a difference between the carbons and the hydrogens. And specifically, we've got a difference of 4 carbons and we've got a difference of 8 hydrogens. And this is going to match up with adding on another unit of our 2-methyl 2-chloropropane where we substitute it on, so we end up with just the methyl propane added on overall. So this could be substituted on. So we're going to get a double substitution overall. So let's start by drawing out this organic product. So there are a couple different options for
our new compound. So we could either have this substitution here, like so, or if we draw out the same compound again, so we've got our quinol base, we've got our group 1 like here, we could substitute it up in this position overall. And you might be able to draw some other configurations, but they all end up rotating or flipping back to these two configurations overall. So the mark is for drawing one of these structures. The student is told by a friend that the iron trichloride catalyst is not needed because quinol is more reactive than benzene overall. And we need to explain why the student's friend is correct. And we can draw a diagram to support our answer if we want to. So here is our structure of the quinol, where we've got these two hydroxy groups directly bonded onto that benzene ring. So what I'm going to do is I'm going to start by drawing out the benzene ring in a slightly flatter configuration. Now I'm just going to draw the outside carbon atoms here, and what I'm going to add on now are the p orbitals. And I'm going to use this to show the overlap above and below the ring of the p orbitals. And this is where the spare electron per carbon is held. We get this overlap above and below the ring. And this is going to cause this ring of pi delocalization here. Now, what happens if we add the two oxygen groups on with the quinol? So I'm going to add them either side, like so. And I didn't draw out the hydrogens for the original benzene because it's skeletal formula, but I've drawn in the whole hydroxy group here for the quinol. And what we know about oxygen is that this atom of oxygen within this hydroxy group bonded directly onto the ring has got two bonding pairs, but it's in group 6, so it's got 6 outer shell electrons. Therefore, if it's used 2 for bonding, it's also got 2 lone pairs. And one of these lone pairs is going to be held in a p orbital that is in the same plane as the p orbitals from that benzene ring. Therefore, we're going to get some partial delocalization into that ring. So we're adding more electron density into the ring overall. So let's write these bits down to start off. So we've got lone pairs of electrons on the oxygen, and these are from the OH and quinol. And these are going to partially delocalize into the ring overall. So this is adding electron density into the ring, therefore making it more reactive overall. So no catalyst is needed. Therefore, this makes the quinol more susceptible to attack from an electrophile. So we've got more electron density in the ring, therefore we're going to be more susceptible to an attack from a positively charged electrophile or a slightly positively charged electrophile, so we can induce dipoles easier overall. And for this question, there's 1 mark for mentioning the lone pair of electrons on the oxygen, which we've also shown here in our diagram. There's 1 mark for mentioning that these are partially delocalized into the ring. Again, we've shown this in our diagram above. And the final mark is for mentioning that this makes the quinol more susceptible to attack from an electrophile overall. 4-nitrobenzoic acid is an important compound in chemical synthesis. The flowchart below shows a synthesis involving our 4-nitrobenzoic acid. So we've got our 4-nitrobenzoic acid here, and we've got a first step leading to compound F, then a second step leading to a product. And for the first part, we need to state suitable reactants and conditions for step 1. So that's this first step here. So let's look at the differences between our 4-nitrobenzoic acid and our compound F. So we can see that on compound F, we've got an ester group overall. Therefore, this reaction for step 1 is an esterification reaction overall. And for this esterification reaction, we're going to need some concentrated sulfuric acid, and that's acting as both a catalyst and a dehydrating agent. And we're going to need an alcohol in order to react with this carboxylic acid group. And the alcohol we need is derived from this section. So we've got 2 carbons. Therefore, we're going to need ethanol, which has got the structural formula CH3CH2OH overall. And in order to get the mark for this question, you need to list both the sulfuric acid and the ethanol in order to get that 1 mark overall. So you need both of these for the mark for this part. And we are told that in step 2, the nitro group in compound F is reduced by tin and concentrated hydrochloric acid. And for this question, we need to write an equation for this reduction of compound F, making sure that we show the structures of any organic compounds which are involved here. We've got our reduction reagents here, and this NO2 group is going to be reduced to an NH2 overall. So we're making an aromatic amine in this question. So let's start off our equation. So we'll start off by drawing out our compound F for our first part of the equation overall. Shown like so. So we've got our ester and then we've got our nitro group. And we're forming the aromatic amine version. So our NO2 is going to turn into an NH2 overall. So that's shown here. And we can represent these reduction agents by using a square brackets with a hydrogen. And this is the key reactant from these reducing agents overall. And we're going to produce another product as well, because we're going to need a second product which contains some of this oxygen, which we've used to reduce our compound to the NH2. And it's got to be a small molecule that's produced here. And for this reaction, we produce water overall. So now we just need to balance this all up. So if we're producing water and we've lost the 2 oxygens from here, we're going to need to put a big 2 in front of our water in order to have the same number of oxygens from these parts here. We don't need to worry about these oxygens because they've stayed the same throughout, so we don't need to include them in our counting for this question. So now let's count up how many hydrogens we've got on the right-hand side. So we've got 4 from the water and 2 from the amine. Therefore, we need 6 molar equivalents of our reducing agent overall for this equation. So now we've drawn out our organic structures and we've balanced the equation. So 1 mark is for drawing out both of the structures. So you need to have both of these organic structures in order to get that 1 mark. And the second mark is for balancing the equation correctly. Alpha hydroxy acids are naturally occurring acids often used as cosmetics. The flowchart below shows some reactions of an alpha hydroxy acid with this formula in specific. And we need to fill in the boxes to show the organic products of reactions 1 and 2, clearly showing the relevant functional groups. So to clearly show our relevant functional groups, we either need to draw our structures as a structural formulae or displayed formulae, or a combination of the 2 as shown over here overall. So let's start by looking at reaction 1 to start us off. So we've got our alpha hydroxy acid here, and we can see that we've got an alcohol functional group and a carboxylic acid functional group. So these are going to be the key groups which we're looking at to see if they react or not. So in reaction 1, we've got a carboxylic acid with some sulfuric acid, and all of this is being heated. And these are the reagents for our esterification reaction overall. And this means that we're going to get a reaction with the alcohol from our AHA and with the carboxylic acid from our reagents, and this is a sulfuric acid catalyst overall for this one. So let's draw out the structure of our product for this reaction. So we've got our carbon centre, and I'm going to start by drawing on the parts of our AHA which have stayed the same. So our acid has not reacted in this reaction. We've still got our carbon chain here. I'm just drawing it exactly the same as it was shown in the structural formulae to keep things easier and neater. And then now we're going to have our ester bond. So you can either draw this out in full displayed formula or structural formulae is also fine. So I'm going to draw it in structural formulae where we use the COO, the COO, to represent the ester bond, which looks like this overall. And that is our COO for the ester. So that was our reaction 1. Let's take a look at reaction 2 now. So for reaction 2, our reagents are sodium bromide with sulfuric acid again, and this is all being heated. And these are the reagents for a nucleophilic substitution reaction. So we're going to be substituting the alcohol from our AHA with a bromide ion from the sodium bromide. And this sulfuric acid is again acting as a catalyst to help substitute out the hydroxide with the bromide overall. So let's draw out the product for this reaction. So again, I'm just starting by drawing out the bits which have stayed the same, which have remained unreacted. So this includes the acid group and the carbon backbone. And now we've substituted out our alcohol with a bromide for this question. And in order to get the 2 marks, it's 1 mark for our first structure from reaction 1 and a mark from the structure from reaction 2 overall. Give the full systematic name for compound G, which is shown here below. So let's start by drawing out compound G in a more detailed display formula so that it's a little bit easier for us to name. So I'm going to start by drawing in the double bond. We've then got our carboxylic acid group, and let's add in our hydrogen here. And we've got another hydrogen up here, and then an ethyl group overall. So we've drawn this out. So now what we want to do is we want to try and identify what our main functional groups are. So we've got an alkene here, and we've got a carboxylic acid. So we need to find the longest carbon chain, which includes all of these functional groups. So this one, we've got a 5 carbon chain overall. So therefore, we've got some form of pentanoic acid from this carboxylic acid bit, but because we've got an alkene, we've got to have some form of a pentenoic acid. So a pentenoic acid. And we need to specify exactly which carbons the alkene bond is between. So whenever we've got a carboxylic acid, because this functional group always has to be on the end of a carbon chain, we always label that as carbon number 1. So let's number the rest of the carbons in the chain. So we can see from this that our double bond is between carbons 2 and 3. So therefore we go the lowest number, and this is going to be pent-2-ene oic acid overall. And then the last thing to bear in mind is that when they've drawn it out in this crab structure here, we can see that across this double bond, we've got some EZ isomerism overall. So because of the double bond, we've got fixed displayed formulae here because we've got no rotation around that double bond. So it's fixed in space. So we need to look and see which are our high priority groups and whether they're on the same side or the different side of that double bond. And that's using our Carn-Ingold-Prelog rules in order to identify whether we've got E or Z. So our highest priority group is going to be the acid group, and that's because we've got the carbon and then the oxygen is the next along, and that's got a higher atomic number than this second along carbon over here. So we've got, that is our first priority, this is our second priority, and these hydrogens are both of equal third and fourth priority there. And what we can see is our two highest priority groups are on opposite sides of that double bond. Therefore, we've got the E isomer. So just to finish off our name, we just put an E at the front. This can be in brackets or just written normally. And overall, our name is going to be E-pent-2-ene-oic acid to finish that off. Compound H is a stereoisomer of compound G, which is shown here to the right. And for this question, we need to suggest a structure for compound H and draw the repeat unit of the addition polymer that can be formed from compound H as well. So let's start with thinking about the structure of compound H. So we can see from the structure of compound G that our two highest priority groups are on opposite sides of the double bond. So we've got the E isomer for compound G. And we have the stereoisomers across this double bond due to them being fixed. So the double bond means that the bond is fixed, so it can no longer rotate freely like a single bond. Hence, the atoms are fixed in space in this configuration. So if we've got the E stereoisomer for compound G, then compound H must be the Z isomer. So we just need to flip one side of the double bond. So I'm going to flip this side on the right here. So we're just swapping those over so that our two highest priority groups are now going to be on the same side of that double bond overall. So just like this here. And there's our Z isomer for compound H. So now let's draw the addition polymer for this one. So in order to draw the repeat unit of the addition polymer from compound H, we can just imagine breaking one of these double bonds and it opening up to sort of form bonds onto the other sides of the carbon. So we're opening up this double bond to form bonds either side of the carbon so that this unit can then repeat down a chain. So let's have a go at drawing this out like so. So our same structure we had before, and then we're opening up that double bond to form bonds either side for this one. And we need to show these bonds in order to get the mark for this question. So there's one mark for the structure of compound H and one mark for the structure of this addition polymer, but we just need to make sure that we show these bonds, and that's just to show that this unit is repeating along the chain. And we could draw brackets and put an N outside the brackets if you'd like, but in this question you don't get any marks for it because we've already identified that we've got the repeat unit overall. We are then told that the addition polymer from above is used widely in industry overall, and increasingly waste polymers are being processed as a more sustainable option than disposal. So they're processing them instead of just throwing them away. And we need to identify two methods for usefully processing waste polymers that does not include recycling overall. So because we've got an organic hydrocarbon-based compound, and we know that when we burn hydrocarbons, when we combust them, we get a lot of energy because there's a lot of energy stored within these bonds. So one way which we could usefully process waste polymers could be the combustion of them for energy production. And we need to make it very clear that we're combusting them for the production of energy. So we're actually using the energy from this combustion rather than just saying burn the polymer. So we need to make it clear why we want to burn that polymer to link it into the question where we're usefully processing them. So that's one method. And another method could be as the use as an organic feedstock overall for the production of plastics or other organic chemicals. So the production of plastics or some other organic-based chemicals. So what this means is that we could use our waste polymer as a starting point, so sort of like the food to make the plastics and all other organic chemicals there. So as the starting point overall, instead of just throwing them away. And for this question, it's 1 mark for each method. A student synthesizes a sample of the alpha hydroxy amino acid J, shown below, using this reaction scheme, and we're starting from propane 1,2-diol. So in this reaction scheme, we've got 2 different steps to go all the way from propane 1,2-diol to our alpha hydroxy amino acid J. And for this question, we need to state a suitable oxidizing agent for step 1. We need to write an equation for step 1, and we need to outline the mechanism for step 2, making sure that we show our curly arrows and any relevant dipoles in the mechanism. So for step 1, we're oxidizing our diol and we're producing a compound which contains a carboxylic acid and a ketone here. Therefore, our suitable oxidizing agent is going to be our acidified potassium dichromate. So acidified, and we could use, for example, some sulfuric acid to do that. And then we need our potassium dichromate, which has this formula here. And our equation for step 1, we need to draw out the structure of propane 1,2-diol just to make that clear why that oxidation is occurring and to make it consistent for our equation. So I'm going to do this in skeletal formula to keep it consistent with the product that's being supplied for this question. So we've got propane, so we've got 3 carbons in our backbone, and then we've got an alcohol group on carbon number 1 and on carbon number 2 there. And for our product, we've formed a compound which has got a carboxylic acid on the end and a ketone on carbon number 2. And this is because when we've oxidized our propane 1,2-diol, we've oxidized a primary alcohol fully to this carboxylic acid, and our secondary alcohol has been oxidized to this ketone here. So therefore, for our oxidizing agent, which we're representing using square brackets with an oxygen in the middle, we're going to need 3 equivalents. So we need 1 equivalent to go from the secondary alcohol to that ketone, and then we need 2 to go all the way from the primary alcohol to the carboxylic acid, because if you oxidize your primary alcohol, you first go to the aldehyde and then you get to that carboxylic acid. So there's 2 levels of oxidation there, hence we need 2 equivalents of that oxidizing agent. And for each alcohol you oxidize, you produce a molecule of water as well. So in total, we've produced 2 molecules of water. And you could also check this by counting up your atoms and making sure that you've got the right number of oxygens, hydrogens, and carbons in total. So we've done these 2 parts here. So now we're going to have a go at outlining our mechanism for step 2 overall. So for step 2, we're going from our carbonyl-based compound to our alpha hydroxy amino acid compound J. And we're using our sodium tetrahydridoborane, which is a strong reducing agent overall. So the first thing to note is that this is going to be a reduction reaction. And as we can see from the difference in our structures, we're going to be reducing this ketone back to a secondary alcohol overall. And this is the reagent which we use to reduce carbonyl, so to reduce aldehydes and ketones. And that's because it's a source of hydride ions. So let's have a go at drawing out this mechanism. So I'm going to start by drawing out our carbonyl compound, like so. And then I'm going to add in a dipole into our carbonyl bond. And this is going to show exactly why this hydride ion is going to want to attack this carbon centre. It's because it's slightly positive due to the polar bond. So our first arrow is going to be from that hydride, from that negative charge on the hydride, so that represents the electron source, so we've represented that we're flowing those electrons to that slightly positive carbon centre. And then this causes one of the bonds between the carbon and the oxygen to break, and a pair of electrons to flow onto that oxygen. So then our intermediate is going to look like this. We've still got our carboxylic acid, and now we've got a negatively charged oxygen because we moved 2 electrons onto that slightly negative oxygen, forming this full-on negative ion. We also added in a hydrogen, but because we're drawing this in skeletal formula, to simplify things, we don't need to show that hydrogen here, but you could draw it out in full displayed formula if you'd like, showing that hydrogen. And now we have a reaction with our acid. So this is the second step of our reaction, where our negative oxygen is going to be attracted to the positive proton. And now we've formed our compound J, our alpha hydroxy amino acid overall. So we've added on a hydrogen and we've reduced our carbonyl down to a secondary alcohol. And for notes, this was a nucleophilic addition reaction. So it's a nucleophilic addition mechanism for our reduction reaction. And for this question, there is 1 mark for identifying the oxidizing agent for step 1. There's 1 mark for writing the equation for step 1. And then there's a mark for drawing the curly arrow from that hydrogen hydride ion to that slightly positive carbon centre in our mechanism for step 2. And then there's a mark for drawing the curly arrow from one of the double bonds to that oxygen, but we also have to have that dipole there in order to get this mark. So there's the bond for the second arrow, and it's also for that dipole. So you have to have both of those bits in order to get that 4th mark. And then the final mark is for drawing our intermediate and the arrow from that negatively charged oxygen to our positive hydrogen ion there. And that's how we get the 5 marks for this question. The reagent used in step 2 of the synthesis, shown below, was sodium tetrahydroborane, and this compound contains the following ions shown here. And for this question, we need to draw a dot and cross diagram of our sodium tetrahydroborane and give the full electron configuration of our 1+ sodium ion. And we only need to show the outer shells of electrons for this question. So let's start by thinking about the full electronic configuration of our sodium 1+ ion. So if you look in your periodic table, you can see that sodium has got 11 electrons as a neutral atom. Therefore, the electronic configuration of the neutral atom will be 1s2, 2s2, 2p6, 3s1. So there's our outer shell electron. We've got just one because it's in group 1 of the periodic table, and it's in the s block because the outer shell electron is in an s orbital. So when we lose this electron to form a 1+ ion, our electronic configuration is going to be 1s2, 2s2, 2p6 only. And this electron is going to be given to the boron to form that negative ion there, because we've got an ionic bond to think about. So let's draw the rest of our dot and cross diagram now. So we've got our boron, and boron is in group 3 of the periodic table. So that means that it's got 3 electrons in its outer shell. And this is going to form covalent bonds with 3 hydrogen atoms, like so. And then we've got the electron which the sodium has donated. So there's an electron transfer from the sodium to the boron in order to form this ionic bond. And therefore we can form a 4th covalent bond now with another hydrogen, and we've got our negative ion here. And for this question, there was 1 mark for our dot and cross diagram, but we need to be careful here because in order to get the mark, you've got to use different elements to show where each of these electrons have come from. So on my diagram, I've used crosses to represent electrons from the hydrogen, dots to represent electrons from the boron, and then just a circular outline to represent the electron from that sodium there. And then our second mark is for the full electronic configuration of the sodium 1+ ion. And to get that, we need to draw it out in full, as I've shown, not using any abbreviations with noble gases or helium. Compound K is an alpha hydroxy amino acid that is often used in chemical face peels. A student wishes to identify compound K from this list of compounds below. So we've got glycolic acid, malic acid, mandelic acid, and pantoic acid. The student isolates compound K and analyzes a sample of the compound via titration. And here's the method for our titration here with our key values. So the student dissolves 1.89 grams of compound K in water and makes the solution up to 250 centimeters cubed in a volumetric flask. The student then titrates 25 centimeters cubed of this solution with 0.150 moles per decimeters cubed of aqueous sodium hydroxide. And we are told that 18.8 centimeters cubed of sodium hydroxide was required for complete neutralization. So we need to use these results in order to identify compound K from this list above, and we need to show all of our working here. So we need to show all of the different steps overall. So let's start by working out some moles. So we've been given quite a lot of information, so we need to find a suitable starting point. So in order to identify compound K, we're going to need to have a molar mass overall. So we need to work our way back to get that molar mass of K. So the first thing which we can do is work out the moles of our sodium hydroxide that have been used in the titration overall, because we've got our volume and we've got our concentration. So the moles of sodium hydroxide is equal to the volume times by concentration. So we just need to make sure that we divide our volume by 1,000, and that's so that we're converting it into decimeters cubed, which is the appropriate unit because that matches up with the concentration units. This multiplied by 0.15, and this gives us a moles of 0.00282 overall. So now we need to use this to work out the moles of the acid that we've got. So each of these compounds are alpha hydroxy amino acids. So we can see that they've all got a carboxylic acid group in them. And we can see that from this list, we've got 3 monoprotic acids and 1 diprotic acid. So because the majority of these are monoprotic, it will be a sensible assumption to assume that we've got a 1-to-1 ratio overall. So for now, we're going to assume that our ratio of the acid to the sodium hydroxide is 1-to-1. Therefore, our moles of the acid in the 25 centimeters cubed, because that was what was used with the titration, is going to be also 0.00282 moles overall. So now we've worked out how many moles of acid we've got from the 25 centimeters cubed. So we need to use this now to work out how many moles of acid we had in our 250 centimeters cubed. So we're working our way back to that original solution which was made up. So we're going from 25 centimeters cubed to 250 centimeters cubed. And to go from 25 to 250, you multiply by 10. Therefore, we also need to multiply our moles by 10 overall. So our moles in 250 centimeters cubed is going to be 0.00282 282 moles. So now we can work out the molar mass of K because we've got the mass which we dissolved into the solution, that's 1.89, and we've got the moles from our 250 centimetres cubed solution. So that's mass over moles there, so we've got 1.89 grams divided by 0.0282 moles, and this gives us a molar mass of 67.0 grams per mole. So what we want to work out is if this matches up with any of our acids from the list. So because we've got quite a low molecular mass, I'm going to start by seeing if this matches up with the smallest acid that we've got. So that's glycolic acid here. So our molar mass of glycolic acid, if we work our way along, is going to be 1 from the hydrogen there, plus 16, plus 12, plus 2, plus 12, plus 2 lots of 16, and plus another 1. And this is going to give us a value of 76 grams per mole. Now this is greater than our value that we calculated for our molecular mass. And glycolic acid is the smallest acid out of each of the monoprotic acids. So this tells us that we must have a diprotic acid. So we must have a slightly different ratio of our acid to our sodium hydroxide. So therefore our acid must be diprotic, and this will therefore affect our ratio, because now instead of having a 1-to-1 ratio of our acid to our sodium hydroxide, we now have a 2-to-1 ratio instead. Therefore, our moles of the acid will be halved in total, which means that we can double our MR. So we can times this by 2, and you can work this all the way through as well, and this gives us 134 grams per mole. Now we've only got one diprotic acid from the list, so our answer must be malic acid, and as you calculate the molar mass of malic acid, this is also 134 grams per mole. So we've got two different ways of checking that our answer was correct. And for this question, there was 1 mark for working out the moles of sodium hydroxide using that titration. And then the second mark was for working out the moles of the acid in 25 centimetres cubed and the moles of the acid in 250 centimetres cubed. So you had to have both of these points in order to get that second mark. Then the third mark was for working out the initial molar mass of K. Then, as we deduced, we figured out that K would have to be diprotic, so the fourth mark is for some statement in there which identifies that none of the molar masses of the monoprotic acid linked up with our answer, therefore we must have the diprotic acid. And then the fifth and final mark was for therefore identifying that K must be malic acid. Cyclohexanone can be prepared in the laboratory by reacting cyclohexanol with concentrated sulfuric acid and sodium dichromate. Ethane dioic acid is added to the reaction mixture in order to react with any of the excess sodium dichromate. This mixture is then distilled, and the impure distillate is going to be a mixture of cyclohexanone and water. We've been given some data here, so we've got our cyclohexanol and our cyclohexanone, and we've been given the boiling points, the density, and the molecular mass for both of these. And for this question, we need to draw a labelled diagram to show how we would safely set up the apparatus for distillation, and we need to describe a method to obtain a pure sample of cyclohexanone from this distillate overall. So let's start by drawing up our distillation diagram. So we're going to start by having a round bottom flask, like so, and this is where our mixture to be distilled will be kept in. We've got to have a heat source below to heat this up, and now let's get to drawing the rest of our distillation setup. So we've got some glassware to connect all of our different bits together, and we need to connect this to a Liebig condenser overall. So we have a delivery tube which runs all the way down to the bottom, and then our condenser will be connected onto this. So it will look something like this overall. And then we have to have some sort of vessel at the bottom to connect our distillate. So I'm going to pick a conical flask. And we need to have a thermometer in our setup. And the thermometer needs to be at the point where the vapours are going to be escaping. And that's so that we're measuring an accurate temperature, and therefore we can determine the boiling points and see which vapours we've got escaping. So labelling this, we've got our thermometer here. We've got our condenser here. We've got a conical flask overall. We've got a round bottom flask, which I'm just labelling as RBF for short. And we've got our heat source. So for example, a Bunsen burner or a hot plate would also be appropriate here. And we also need to label which way the water is going to be going in and out of our condenser. So it's always cold water in at the bottom, and then warm water out at the top here. So we have cold water going in at the bottom, so that when our vapours are travelling down, they then condense at roughly this point here in the system. Because if we had cold water going in at the top, then our vapours would condense at this part, but not fully because they'd still be very, very warm. And then when the warm water is then travelling out, this could then potentially evaporate our liquid again. So it's cold water in at the bottom and warm water out at the top there. So now we need to describe a method to obtain a pure sample of our cyclohexanone from this distillate here. So we need to think about our further purification steps. So we were told that our impure distillate is a mixture of cyclohexanone and water. And what we've got here is we've got an organic compound and an aqueous compound. Therefore, we can use a separating funnel to separate these two out. So we can separate these into an aqueous and an organic layer. And the reason that we can do this is because our cyclohexanone is less dense than water. So we know that water has got a density of 1, and we've been told that cyclohexanone has got a density of 0.948. Therefore, it's less dense than the water, so our cyclohexanone will be the top layer, and the water, that aqueous layer, is going to be the bottom layer. So we're going to use our separating funnel, and we're going to tap off the different layers there. We can collect these into conical flasks, we can label them so that we don't get them muddled up. And now, once we've got our organic cyclohexanone layer into its conical flask, we can add a small amount of magnesium sulfate to our cyclohexanone. And the magnesium sulfate acts as a drying agent. So this will absorb any little bits of water which have been left in that layer, because often when you're tapping off the layers, we could leave behind a small amount of that water in the organic layer. So this magnesium sulfate is just going to mop up any excess water there to make sure that we've gotten rid of all of that water. So then our next step now is going to be to redistill that cyclohexanone to make sure that it's 100% pure in case it contains any leftover cyclohexanol as well. So we're going to redistill the cyclohexanone, and we want to collect the fraction which distills at around about 156 degrees there. But it could be anywhere between 150 and 156 degrees there. And for this question, it is a quality of written communication style question. So what that means is that this question is banded. So we've got band 1, band 2, and band 3 for our marks. So rather than just being 1 mark per point, we've got to have an answer which includes some information on our apparatus for distillation and at least a part of a method for collecting a pure sample of the cyclohexanone in order to get into the top bands overall. And some of the indicative points that we need in order to gain some marks and get into the top band for this question are going to be this detailed diagram here of our distillation. So including our round bottom flask, a collection vessel, having our condenser with the correct direction of water flow, having a thermometer with that bulb at the correct exit point for the vapours there as well, and having a heat source, and as well for this whole system to be open. So to have an open system is really important because we need to make sure that these vapours are allowed to exit the system in order to be condensed. And for our further purification steps, some more of these indicative marks are going to be using our separating funnel, where we're also going to be shaking the separating funnel and allowing the layers to settle. So allowing the layers there to settle. Tapping off those layers and recalling that they will be separate layers due to their densities. A step to do with the drying of that cyclohexanone, and specifically in order to get into those top bands, we want to be mentioning that we use magnesium sulfate as our drying agent. And then mentioning the redistillation of that cyclohexanone and the boiling point that we're going to be collecting our fraction at overall. And in order to get maximum marks for this question, we need to have a full detailed diagram with all of these details that I mentioned, as well as at least 2 detailed steps for this further purification. Ethane dioic acid removes excess dichromate ions as shown in this equation below. So we've got our ethane dioic acid reacting with the dichromate ions and some acid, and we're producing carbon dioxide gas, some chromate in oxidation 3+ ions, and some water. And for this question, we need to suggest how we can tell when the excess dichromate has completely reacted with that ethane dioic acid. So the key thing with this reaction is that we're producing carbon dioxide, which, as I mentioned, is going to be a gas. Therefore, in this reaction, we're going to see some fizzing, some bubbling, some effervescence. So when our excess dichromate has completely reacted with the ethane dioic acid, we're going to get a lack of further effervescence. Or we could also say that our fizzing or bubbling stops. So for this question, we just need to mention that some sort of fizzing or bubbling stops in order to get that mark. For the preparation of cyclohexanone, using our cyclohexanol with some concentrated sulfuric acid and sodium dichromate, we can monitor this course of reaction using thin layer chromatography, also known as TLC. And for this question, we need to outline how TLC could be used to monitor the course of this reaction. So what we can do is we can take some samples from the reaction mixture at regular intervals. And then with these samples, we can spot them or run them on a TLC plate with a cyclohexanol and cyclohexanone control. So what we will have is we will have a TLC plate looking something like this. We'll have our line, our pencil line here, and then we'll have a spot for our cyclohexanol control, a spot for our cyclohexanol control, and then various reaction mixture spots along the plate, and you'll probably use several plates. And then we will get our pattern for our cyclohexanone and our cyclohexanol, which could look something like this. And then what will happen is, throughout our reaction, as our cyclohexanol reacts, we will start to see less of the cyclohexanol and more of the cyclohexanone. So you might see a mixture of the two, and then as our reaction is nearing completion, we will only see spots for cyclohexanone there. And then, in order to get both the marks, there's one mark for mentioning that we have to take some regular samples from this reaction mixture, and then the second mark is for mentioning that we're going to spot these on a TLC plate along with our controls, and that's so that we can compare our reaction mixture to these controls to see which out of the cyclohexanone or the cyclohexanol we've got in our mixture. For the second mark, you could also mention about using RF values to confirm which samples we've got as well. For the reaction where we produce cyclohexanone from our cyclohexanol with concentrated sulfuric acid and sodium dichromate, we need to plan an experiment that would allow the student to confirm the identity of our pure organic product, and we need to do this by means of a chemical test. So our organic product here is going to be the cyclohexanone, and what we know about this compound is this ends in ONE, so this ends in one, which means that it's going to be a ketone, which was produced by the oxidation of our cyclohexanol. So this was a secondary alcohol, which was then oxidized with our concentrated sulfuric acid and sodium dichromate to produce a ketone. And we know that our ketone contains this carbonyl bond. Therefore, we can confirm our identity of the pure organic product by first reacting our sample with some of our 2,4-dinitrophenylhydrazine, which I've shortened here to 2,4-DNP. This is also known as Brady's reagent, and they would allow either of these for the mark for this bit. And what happens when we react our sample with this 2,4-DNP is we're going to get an orange precipitate due to the presence of that carbonyl bond. And the key thing here is that we're producing a precipitate. So now that we've got our precipitate, we can recrystallize this. And we're recrystallizing our precipitate in order to purify it. And then we can determine the melting point of our precipitate. We can do this using a melting point machine with some capillary tubes for our sample. And then once we've determined the melting point of our sample, we can then compare the melting point to a known value for cyclohexanone. And we could get this known value from a textbook, or we could look it up online from a reliable website. And in order to get the 3 marks for this question, the first mark was for mentioning that we're going to react our sample with 2,4-dinitrophenylhydrazine, and they would also accept if you put down 2,4-DNP or if you put down Brady's reagent. The second mark is for saying that we need to then recrystallize our precipitate and determine the melting point. So you need to have both of these points in order to get that second mark. And then the third and final mark is for stating that we need to then compare our melting point to a known value or a known library for cyclohexanone. A chemist isolates compound L with an empirical formula of C3H6O and sends a sample for analysis. The analytical laboratory sends back the following spectra. So we've been told that we have a mass spectrum with a molecular ion peak at mass over charge ratio 116.0, and we're given some proton NMR spectra. We've got one with no D2O, and we've got one with D2O added. We are also told that the numbers next to each signal represent the number of protons responsible for that signal overall. And we can see our splitting patterns, and we've got our chemical shift values. We are also given a carbon-13 NMR spectrum, and we need to use all of this information provided to suggest a structure for compound L. So let's start by working out the formula of our compound L so that we can start to comprise a structure. So we've been told that our empirical formula is C3H6O, and we've been given the molecular ion peak from our mass spectrum. And we can use this data to therefore work out what our molecular formula is. So our molecular ion peak is the same as the MR for the compound. So what we need to do is work out what the empirical mass is, and then see if this is the same as the molecular mass or if it's a different factor. So our empirical mass is going to be 3 lots of 12 plus 6 lots of 1 for the hydrogen plus 16, and this is equal to 58. So then if we divide 116 by 58, we can see that we've got a factor of 2. Therefore, we need to multiply our entire empirical formula by 2 to get our molecular formula. So therefore, our molecular formula is going to be C6H12O2. So we worked out already that our molecular formula is C6H12O2. So now let's have a look at our carbon NMR spectrum so that we can get a bit more information about our structure. So with our carbon NMR spectrum, the number of peaks is equal to the number of carbon environments there. So what we can see on our spectrum is that we've got 5 different peaks overall. So we've got 5 peaks on our spectrum, therefore we've got 5 different carbon environments. And because we've got 6 carbons in our compound, what this tells us is that we've got to have some situation where 2 different carbons are in the same environment, so some aspect of symmetry. For example, maybe something like this, where you've got 2 carbons bonded to the same carbon, where they're in an identical environment there. So now, if we look at the peaks and their chemical shift values, we can start to work out a little bit more about the carbon environments within our compound. So the peaks on the right-hand side of the spectrum are going to be from alkyl chains overall. And these are going to be relatively shielded, which is why they appear on this right-hand side. But we've got one peak here on the left-hand side, which is very de-shielded. And this peak, which corresponds a chemical shift value of 213 ppm. If we have a look at that on our data sheet, this corresponds to the carbon from a carbonyl bond overall. Now we don't know whether this is going to be from an aldehyde or a ketone at this stage, or even potentially a carboxylic acid. But what we do know is that we've got that carbonyl bond there. So now what we've worked out is that we've got 5 carbon environments, and that we've got a carbonyl bond from the peak at 213 parts per million there on our carbon-13 NMR spectrum. So now let's have a look at our proton NMR spectra so that we can put our structure of compound L together. So we've got 2 spectra here. We've got a normal proton NMR spectrum run in a normal solvent, and we've got a proton NMR spectrum where D2O has been added. So deuterium is an isotope of hydrogen, and it's a heavier isotope of hydrogen. And when you add D2O to your compound and then run your spectrum, the deuterium replaces any protons which are bonded to either an oxygen or a nitrogen. So some sort of either alcohol group or amine group we're focusing on here. And due to the properties within the nucleus of the deuterium, it does not show up on an NMR spectrum once it replaces the protons bonded to oxygens or nitrogens. So what this means effectively is if you're comparing these two spectrums together, if you do have either an alcohol group or an amine group within your compound, when you look at the spectra with D2O added, the peak responsible for either your alcohol or your amine will disappear because that hydrogen has been replaced by a deuterium, so it no longer shows up in the NMR spectrum. So thinking about our compound specifically, we had our molecular formula C6H12O2, so we're only really thinking about the potential of an alcohol group in this compound. And what we can see is if we compare our two spectra, we've got 5 peaks when we've got no D2O, and when we've added our D2O, one of our peaks has disappeared. So it's this little peak here that's disappeared that was originally responsible for 1 hydrogen, and it's disappeared when the D2O has been added. So this tells us that this peak here is responsible for the hydrogen bonded to an oxygen in an alcohol group there. So now let's start to look at the environment and the splitting for the other peaks so that we can get the rest of our structure. So I'm just going to be working off the bottom spectra because there's a slightly bit more space there. So let's work left to right here. So with our peak at around about 3.8 ppm, we've got a triplet, and we've been told that this represents 2 hydrogens. And if you look in your data sheet, the environment which corresponds at around about 3.8 ppm is when you've got a proton that's bonded to a carbon that is single bonded to an oxygen. So we're looking at this proton here, this one. But because we've been told that this represents 2 protons within this environment, there must be 2 different hydrogens. So this is what our environment looks like for this situation. And therefore, if we've got, for our carbon, 2 bonds to hydrogen, a bond to an oxygen, then that means that this carbon must be bonded to another carbon. So that's going to be our first look. And now if we take a little look at the splitting, we can see that we've got a triplet. And from the n+1 rule, we know that n represents the number of different hydrogens bonded to the adjacent carbon there. And then you just add 1 on, and that's going to be your splitting pattern for that particular environment and that peak. So because we've got a triplet, if we take away 1, that means that there must be 2 hydrogens bonded to the adjacent carbon. Therefore, we can put 2 hydrogens in here, and now we can see our full view for that environment overall. So I'm just circling the hydrogens which are in this environment. Now, the next peak along is not in this spectrum with the D2O added, but we identified it on the spectrum above. This is going to be our OH. So now, looking at the next peak along, we've got this peak here, which is at around about 3.1 parts per million there. And we can see that we've got another triplet, and this also is representing 2 hydrogens. So if we want to think about the particular environment for this one, this chemical shift value, if you look on your data sheet, corresponds to hydrogen, which is bonded to a carbon, which is then bonded to a carbonyl bond, like so. And because we've got 2 hydrogens in this environment, that must mean that we've got to add another hydrogen in there, like so. So we've got the 2 hydrogens in this environment here. So now let's have a look at the splitting pattern so that we can build up the rest of that environment. So we've got a triplet, and referring back to our n+1 rule,
that must mean that we've got 2 hydrogens on an adjacent carbon. Therefore, because we can't add 2 hydrogens onto this carbon here, this tells us that we've got another carbon with 2 hydrogens bonded on, like this. Now, there is a potential to have a hydrogen here, and we could have an aldehyde, or this could be bonded to a carbon and could be a ketone. So we'll leave it at this for now, and then we can always come back and modify our structure later on if need be. So the next peak then, which we want to look at, is this one here. So we've got our multiplet here, or from the zoomed in, we can see we've got 1, 2, 3, 4, 5, 6, 7. So that's going to be a septet, and that's at around about 2.7 ppm there. And we're told that this represents 1 hydrogen. So this chemical shift value is actually very close to our previous peak. And that's because we've actually got the same environment overall. So what we've got is we've got a hydrogen that's bonded to a carbon that's bonded to a carbonyl bond. So we've got the same thing as before, but we've got a slightly different situation going on. So we're looking at a different environment, but appearing at the same chemical shift due to the hydrogen being bonded to a carbon bonded to that carbonyl bond. But this time, we've told that this environment only contains just the 1 hydrogen here. Therefore, this carbon must be bonded to other carbons. And supporting this fact is that we've got a septet here. So using our n+1 rule, what that must mean is that our carbon is bonded to carbons which are bonded to 6 hydrogens. And there's only one way which we can get that to work with our bonding, and that's by having 2 methyl groups bonded there to that carbon. So therefore this carbon has now got 2 adjacent carbons, each containing 3 hydrogens. That's 2 lots of 3, that makes 6. You add 1 and you get 7 there, so that matches up with our septet. So looking at our last peak now, we've got a doublet representing 6 hydrogens at a ppm value of around about 1.1 or 1 ppm there. So we've got that doublet representing 6 hydrogens. And if we have a look on this structure here, which we just drew out, that must be from these hydrogens here. So they're hydrogens and they're in the same environment. So I'll just underline those in purple. And this is going to correspond then to those hydrogens there. And that matches up with our symmetry aspect, which we mentioned when we were going through the carbon-13 NMR spectrum. Now, the last thing to look at before we move on to building up our structure is what's happened to the rest of this carbonyl bond. So I said previously that this carbon, we can see we've only got 3 bonds there, and that's the case with a few of these different chunks because we've got to actually build up our molecule. But this carbon can either be bonded to a hydrogen or a carbon in this situation. However, if it was going to be bonded to a hydrogen, we would see another peak in our spectrum. And we'd be seeing a peak at around about 9 or 10 ppm if that was an aldehyde. However, we don't have that peak. Therefore, this tells us that we've got a ketone. So this carbon is bonded to another carbon there. So now we can put together all of this information to start to think about our structure. So building up our structure now, what we know is that if this carbonyl bond must be a ketone, then this carbon has to be bonded to another carbon. So that would then therefore make sense if this was the other side of that. So we've got our carbonyl bond in the middle, with this section one side and this section other side. And then now if we compare this section to this section here, we must have these two being the same. And therefore we've got this at the end with our OH, which we identified from before. So now let's draw this out in full and think about where we can get the marks for this question.
So we identified that we have that carbonyl bond, and to the one side we had a carbon which was bonded to two methyl groups. That's where they've got two carbons and two hydrogens in the same environment. And then that carbon also had a hydrogen bonded to it. And then to the other side of that carbonyl bond, we had two CH2s, and then we had an alcohol group. So let's count up our numbers of atoms and check that it matches up with our molecular formula. So we've got 1, 2, 3, 4, 5, 6 carbons. We've got 1, 2 oxygens. And for our hydrogens, we've got 6, 7, 9, 11, 12. So that all matches up with our molecular formula. And just reflecting back on our carbon NMR, let's check how many carbon peaks we've got. So for our carbon environments, we've got 1, 2, 3, 4, and then these two carbons are in the same environment, so we've got 5 overall. And it's always a good idea with these questions to go back and check at the end that you've got the right number of environments to match up with your peaks, because sometimes when we look in at the details, we forget that when we're slotting things back together, that we need to get things the right way round and bonded the right way in order to match up with those number of environments. So it's easy to get the right functional groups, but the wrong layout overall. So it's always worth bearing that in mind to go and check that. So this question is a quality of written communication question. And what that means is that rather than being 1 point per mark, we instead have our banded marks for this question. So you've got bands 1, 2, and 3. And in order to get into that top band and to get the full 6 marks, we need to be having the correct structure to start off. We need to have fully analysed all of our proton NMR peaks as we did on the previous page. And we need to have at least 2 supporting statements. So for these supporting statements, one of them would be for our working out for the molecular formula, which we did on the previous page. One of them is for mentioning that we have a ketone because of the fact that we have no peak between 9 and 10 parts per million on our proton NMR spectrum. So that would have corresponded to the hydrogen from an aldehyde. So by mentioning that, that's clarifying why we picked a ketone, why we put our structure together in this way. And another supporting statement you could mention is the fact that we have the alcohol with this hydrogen here because we lost that peak from our proton NMR spectrum when we added D2O to that, because the deuterium replaces that hydrogen and no longer shows up in our proton NMR spectrum. Now, to get 4 marks out of the 6, you would need to include the fact that we've got a carbonyl bond and our alcohol group with supporting statements and having a similar structure but slightly different laid out, so not all of the peaks matching up to the correct environments overall. And with this whole question in general, we need to be including all of those points which we had listed on our proton NMR spectrum. So we analysed them in full with the peak environment, so that's from our chemical shift. We looked at our splitting by using the n+1 rule, and we looked at our integration, which was given to us next to the peaks. And looking at all of these different bits of information and putting them together then gives us the structure of L and gets us into the top band to get full marks.